Okay, guys. So then let's continue our discussion and actually finish our discussion on curve sketching. So last time we did a couple of examples on how to graph functions. Now we're just putting all the knowledge that we have learned in this chapter together about derivative and how to use derivative to find information of a function to finally be able to graph. Okay. So here are some suggested steps that you could follow when you want to graph, sketch the graph of any function. Again, these steps, some of these are optional and so on, but the idea is that if you follow these steps and then you put the information together that you will obtain, you will be able to uh, hopefully sketch the graph of a function. Okay, so let me explain these steps and then I'm gonna do a couple of examples and then hopefully that will be enough for you to be able to analyze functions. Okay, so step number one, find the domain. Remember, when you want to work with a function, the first thing that you should do is figure out the domain because you want to know where the function is defined and where the function is not defined. Okay, so that's very important. So find the domain of a function. And after that, step number two, again, as I mentioned last time, this is an optional step, but if the function has symmetry, it's helpful to know it. Okay, so find the symmetry of a function, and just as a reminder, you do this by plugging in negative x into the function. If it turns out that after simplifying you get back the original formula, so the function itself, this means that f is even. Okay, the function is even, which is which means geometrically that this is symmetric with respect to the y-axis. Okay, so that means that if you only will need to graph half of the graph of the function because the other half you get it for free. Okay, by just using reflections. Okay, but if this doesn't happen, then the other thing that you could do is plug in negative. So again, you plug in negative x. If you don't get back the original formula, sometimes you can factor out the negative out of the entire function and you will get minus a function. If this happens, then that means that the function is odd, meaning that it is symmetric with respect to the origin, okay, the point 0, 0. So this helps. So if your function has symmetry, it helps in the graphing process. Okay, so then another important information to find are the intercepts. Okay, so here we mean the x-intercept and the y-intercept. These are important points to have when you are graphing. For the x-intercept, you find this by solving the equation f of x equals to 0, right? So this is the values that makes the function equal to 0. That's when it crosses the x-axis. And then the y-intercept, you find this by just plugging in 0. So this is the point 0, comma f of 0, okay? The y-intercept is always pretty straightforward to figure out. Okay, so after this, here is one step that is actually very helpful when it comes to actually produce a picture, okay? Even though it's not strictly necessary, I strongly encourage you to do step 4, which is to figure out the sign of the function. This is the function itself, f of x, okay? So this means that we want to solve the inequalities f of x greater than 0 and f of x less than 0. And why is this helpful? What's the benefit in doing this? Well, when f of x is greater than 0, here what you're finding is information of the intervals for which f is above the x-axis, right? Where f is above the x-axis. And similarly, when you find this information, what you're getting here is the intervals where f is below the x-axis. And this is a very helpful information. And actually, when you get to this is very good to know when you're going to graph. And when you get to step 4, you already have everything you need to actually do this. Because remember, how is it that you find, how is it that you solve inequalities in general? the way that we have been doing in class to find, the sign of the first derivative and the sign of the second derivative and so on. So what is it that you do? You find the zeros. This is true for any function when you want to know when a function is positive or negative, okay? So find the zeros of the function. And also remember, you need to take into account the values that makes it undefined. Values that make f undefined. And then once you have these numbers, these values, which by the way, once you get to this step, you already have this information. For example, the zeros of the function. Okay, look at step 3. You had to find those numbers when you were solving for the x-intercept. Okay, so the x-intercepts in step 3 are already the zeros of the function that you need here. The values that make the function undefined, you needed to figure that out up here when you were finding the domain. Remember, the domain is precisely the values that makes the function defined. Therefore, to write down the domain, you need to know what makes it undefined, so you can remove those numbers from the real line. So in step 1 and step 3, you already have the information needed to complete step 4. Okay. And then once you have these numbers, what is it that you do? You plot them in a line, right? So plot these values on a number line. Okay, plot these values on a number line and test the sign, and test the sign in each interval. And test the sign of f in each interval. And remember how you do this by picking a value inside each of the intervals and plugging in, and whatever sign the function f has at the value, that will be the sign on the entire interval. Okay. So, typically in this step, what's going to happen is that you're going to have a picture like this, and then you're going to have some numbers, let's say A, B, C, whatever. And, you may have some signs, that kind of stuff. For example, let's say that you get a picture like this. Typically step number 4 will look like this, where A, B, and C, and whatever are them could be more or could be less, it really depends. But those numbers, A, B, C, etc., you already know them from the previous steps, okay? So in this step, you just need to draw a little line and test the function for, for its sign to see if it's positive or negative. And remember, when you have this sort of picture, the information that this is giving you is that here the function is above the x-axis. Here the function is, let's move this a little bit. Then something that this will read as below x-axis. Again, above x-axis and still above the x-axis. Okay, so this is helpful when it comes to graphing, and it really requires not too much effort. You already have all you need to do this. Okay, so why skip it? Don't skip this. This is gonna help you to put your picture together later on. By the way, notice that so far steps 1 through 4 requires no calculus whatsoever. Okay, these are really, if you will, pre-calculus steps. Okay. All right. Now we start to go into all the steps that do require some calculus. Okay. So something else that's very helpful is to analyze the end behavior of the function. Okay. We want to know what happens when x approaches positive and negative infinity. That's what end behavior is. And also if there are any asymptotes. Okay. Vertical asymptotes or horizontal asymptote or slant asymptotes. Okay. So find all the asymptotes and the end behavior of the function. For example, let me give you here a couple of points. So in the case of vertical asymptotes, we have discussed this. Remember, a number x equals c is a vertical asymptote if and only if when you take the limit as x approaches c from the right or maybe from the left, okay, from the right, or as x approaches c from the left, one of the two side limits, of the function if this gives you either a positive or a negative infinity. Okay? In other words, if when you approach C from one of the sides at least, if the values of the function grow unbounded or decrease unbounded, without bounds, going up all the way or down all the way, meaning positive or negative infinity, then you know that you are in the presence of a vertical asymptote. Okay? Typically, if your function looks like a fraction, right, your candidates here would be zeros of the denominator. Okay? But also remember that there are some functions that don't have to look like a fraction to have vertical asymptote. I think about the natural log function. The logarithmic function, it has a vertical asymptote in the y-axis, right? The line x equals 0. As whenever the argument approaches 0, you're gonna have a vertical asymptote. So keep that information in mind. Okay, so as for vertical asymptote, and then when it comes to the end behavior, okay. So when it comes to end behavior, then the end behavior here really what this means is you need to compute these two limits. So we want to know what happens when x approaches negative infinity. What is the function doing? So this will tell you how to begin the graph. Remember, we graph from left to right. So we want to know how to begin our graph, and also want to know how to finish our graph. So when x approaches positive infinity, what's the function doing? So we want to compute this limit as well. So this is what the end behavior tells us. Okay. Now we know that if one of these limits, so if at least one of these limits, in the end behavior, these limits are infinity. At least one of these limits equals a number. So one of these limits is finite. Say is equal to L. Okay, so if one of these limits is finite, then what we say is that the line y equal L is a horizontal asymptote, right? Then y equals L is a horizontal asymptote. So that's how you find horizontal asymptotes. You just look at the end behavior, and if it turns out that one of these limits give you a number, then you have yourself a horizontal asymptote. Now, if you don't get a number, typically what happens is you're going to get either positive or negative infinity. At that point, you're already it's telling you that it's going to infinity, but we want to also figure out if this is happening in a linear way or not. In other words, do we have any slant asymptote? As the function goes to infinity, looking like a line or not? In pre-calc, you figured out a way to find this, which was for rational functions, which is by actually doing long division. And the condition was that if the degree of the top is one more than the bottom, then you have a slant asymptote, and you find it by using long division, and the quotient is your slant asymptote. Okay, so if we have time today, after I finish graphing, I'll give you an explanation on how to find a slant asymptote for more general functions. Okay, but for now, let's just concentrate on sketching functions so that we don't use too much time on this. It's not really a side topic, but it's really like a topic on itself. So I'd rather discuss graphing function right now. But keep in mind that it's something that we need to say about slant asymptotes. Okay, but at least the limit will be infinity, so you can sketch a reasonable graph, even if you don't know that it will be linear. But for rational functions, you do know. Okay, remember, if the degree of the top is bigger than the bottom by 1, then you have a slant asymptote, and you find it by long division. And the quotient is your equation for the asymptote. Okay, anyways, let's just put a parenthesis on slant asymptotes for now. All right, so we know the asymptotes, we know the end behavior. Now we keep doing more calculus. So this time the derivative enters. And what do we do with the derivative? Well, we find the first derivative because we want to know the critical numbers. Why? Because those are our candidates, remember, for relative extrema. So here in the first derivative, what you're going to do is you're going to figure out the monotony of the function. That means when it's increasing or decreasing, okay? And relative extrema. So remember, monotony means increasing, decreasing. okay, and the relative extrema to see where we have any relative maximum, relative minimum, etc. And also at this point, once you take the first derivative, you want to see if we're going to have any possible vertical tangent line. We haven't mentioned this in class. I mean, we talk about vertical tangent lines right at the beginning, but now in these days we haven't talked about this. But basically, a vertical tangent line, what does that mean? It means that the slope, you have a point on the function at which the slope is infinity. So basically, a vertical tangent line shows up whenever the derivative has a vertical asymptote. Okay, so if you want to know points at which you may have vertical tangent lines, so that's equivalent to say that the slope, uh, you know, approaches positive or negative infinity, which is equivalent to say that f prime has a vertical asymptote. So when you find the first derivative, just take a peek at the formula and think about whether that function that you have, which is just a function, right? If it's gonna have a vertical asymptote or not. Anyways, you need to know how to find vertical asymptotes because we did it. You have to do it for f. Now do it also for f prime. If you find that there is a vertical asymptote and that point is actually a point on the graph of the function, right? It has to be a point on the graph of the function f, then that means that we're gonna have a vertical tangent line. Okay. So slope approaches positive or negative infinity, which is the same thing as saying that f prime has a vertical asymptote, and the point on the graph of f is important. If the point is not in the domain of f, then we don't care about it. Okay. So this is important. I guess let me give you a quick example so you see what I mean. For example, think about the function f of x equals the cube root. Okay, think about this little function here. The domain here is all real numbers, as you all know. Okay, by the way, the graph here. Okay, the domain here is all real numbers, and this is x to the 1 over 3. So if we find the derivative, what is this? It's gonna be 1 over 3 x to the 1 over 3 minus 1, so that's negative 2 over 3. So it'll be 1 over 3 times x to the 2/3. So notice that in particular, our function, right? The function f is defined at 0. However, the derivative is not defined as 0. And notice that if you take the limit as x approaches 0 of the derivative from one of the sides, from either side actually, what's going to happen? We're going to get positive infinity because we have 1 over 0, which is infinity. So know that the limit as x approaches 0, here it doesn't matter one of the in from either side because of the square. We have 2 over 3, but that 2 is a square, so it's going to make it positive. But doesn't matter. Let me just say from the right of f prime, this limit is positive infinity. Okay, so what this is telling us is that x equals 0 is a vertical asymptote of f prime. So f has a vertical tangent line. A vertical tangent line at x equals 0. And indeed, let's take a look at the graph. Let me give myself more space in here. Okay. So let's look at the graph of x cubed. What's the graph of x cubed? This is one of your basic functions, right? So the graph of x cubed is like this. You know, we have an inflection point at 0, 0. So if you find the second derivative, you figure out that there is an inflection point at 0, 0. But I want you to pay attention to what happens there, right? So if you look at, if you want to follow what would be the tangent line, notice that as we, let's say that you pick a point here, right? As we get our points closer and closer to the red point, what's going to happen to the secant lines? They're going to converge towards the y-axis like this. Similarly, if we do it this way, if we get close to 0, 0 from above, with this point from above, once again, the secant lines, they're going to converge to a tangent line. So here, the tangent line, this is a tangent line, but it's a vertical one, okay? So you get this type of information. So basically, you know, when you're graphing a function, if the function has this sort of shape with an inflection point like this, typically you're going to have a vertical tangent line, okay? All right. So we'll do an example today in which we'll have a function that has a vertical tangent line, okay? So that's why I wanted to pause here and give you this little example, just so that you're aware of that. Okay, so we find the first derivative, find the determine monotony, relative extrema, and also any possible vertical tangent lines. After this, what do we do? And remember, along all this way, anytime that you find points that would be on the graph with some property like relative extrema or something like that, you always find the x, but also the y, because we're graphing. So when we actually graph, we want to plot the point. Okay, so it's important. So as you do these steps, you're creating a list of points that will be on your graph. So you may want to have a little table on the side, and then you are putting all of those points on that table. Okay, and label them so you know what they are: maximum, minimum, x-intercept, y-intercept, etc. Okay, and step 7, find the second derivative. Why do we want this? Well, you want this because you want to determine the concavity of the function, right? What is concave up, concave down, and also any inflection points. Okay. Remember that to find the relative extrema in step 6, you have two choices. You can use the first derivative test, which anyways, you're going to have the sign of the first derivative to figure out monotony. So it's very easy to just then use the first derivative test. But you could also then use number 7 to make sure that you did the correct work by using the second derivative test to check that whatever you found in step 6 actually makes sense, the relative extreme. Remember, the second derivative test says if you plug in a point and a stationary point, so a critical number whose derivative is 0, and you get a positive number, that means that you have a minimum, a relative minimum. If you plug in and you get a negative number, that means you have a relative max. Okay? If you get 0, it's inconclusive, so you have to use first derivative test. Okay, but again, that one will be extra because if you already did first derivative test, there is no need to do a second derivative test. So step 7 is important because you use it to find concavity and inflection points, looking at the second derivative, as we have done in class. And then finally, with all of this information, just put it together now, plot, plot all the points that you have found, and then if it's necessary, plot a couple more points if you want to get more information about the graph, like where does it pass through, etc. And then just sketch. Okay. So what I'm gonna do now is let's graph some functions, and the idea is that we're gonna follow these steps, one by one. Again, some of these are optional, but I strongly encourage you, to follow them, and that's gonna guide your work. Okay, so without further ado, let's go and do some examples. So sketch the graph of the function. Okay, and let's see. Let's first start with actually something interesting. Let's start with 2 times x to the 5 over 3 minus 5 times x to the 4 over 3. Okay, so here is a function. And this is not a polynomial function, as you can see. This is actually a bunch of cube roots that we have in here and so on. Let's actually figure out how this function looks like. Okay, so we're gonna take this one step at a time. Let's just follow our list of steps. Okay, all right. So step number 1, we want to figure out the domain. Now notice that this function these are just cube roots, right? And the cube root is defined everywhere. Here you can plug in whatever number you want, positive or negative. That's not going to be an issue. We know these are cube roots, both of these terms, because of the 3 in the denominator. Okay, so the domain here is all real numbers, negative infinity to positive infinity. In other words, our graph has to cover the entire x-axis. and there is no value that we need to worry about when it comes to the function. Okay, domain is done. I'm gonna figure out my symmetry. Okay, so for the symmetry, remember you plug in negative x into the function and then you observe what happens. Let's see. So we plug in negative x, and then we observe what happens. Uh, for example, in the first term, we can see that we have a cubic, so we can factor out the negative out of the cube root. Sorry, we have a cube root. The negative goes out of cube root and survives the 5, because the 5 is also an odd power. So that's negative 2 x to the 5 over 3. And then in the second term, yes, it's true that the negative goes out of the cube root, but then, the 4 that we have over there is going to make it a positive. Or if you want, if you do the 4 power first and then cube root, right, the 4 is going to kill the negative, so that negative is gone. So we have, this is the negative that I'm talking about, okay? The other one is part of the function. So we have negative 5x to the 4 over 3. Okay, so notice that this is not equal to the function itself. So the function is not even. So not even. It's not even. And then notice that if I multiply the function f by negative 1, I'm going to get, yes, a negative 2 in front, yes, but then the 5 will be positive because we need to change the sign, okay? So this guy here will become positive, and that's not what was happening here. So it's not even, it's not odd. So symmetry, well, is neither. Okay, so we don't have symmetry here. So let's move on. At least it's not even, it's not odd, it's neither. So let's move on from here. Step 3, let's find the intercepts. Okay, so for the intercepts, let me find the y-intercept first, because this one is the easy one. It's always easy, right? So you find this by just plugging in 0 into the function, which in this case, we're just gonna get 0. So that's a point 0, 0. Now for the x-intercept, that's another story. We need to solve the equation f of x equals to 0. So that is 2 times x to the 5 over 3 minus 5 times x to the 4 over 3 equals 0. And then when you're dealing with this kind of expressions, remember what you need to do to solve this equation is you need to factor, okay? Don't simplify stuff like by dividing and so on a variable, because then you're going to lose solution, okay? Now you may wonder, how do I factor this? Well, even if you don't have, nice integer exponents, the factoring works the same way, okay? Just look at these numbers, 5 over 3, 4 over 3. Which one is the smallest? That's the one that you want to factor, the term that you want to factor. So in this case, 4 over 3 is the smallest, so I'm going to factor out this term, okay? So I'm going to take out an x to the 4 over 3, and then let's see what's left if I factor this, okay? So let me actually go one line below. So I factor x to the 4 over 3, and let's see what is left. Remember, to factor means that you want to divide every term by this expression. That's how you know what's going to remain inside the parentheses. So the 2 stays. And then if I do x to the 5 over 3 divided by x to the 4 over 3, all you're doing is subtracting the exponents. So 5 over 3 minus 4 over 3 is 1 over 3. So there is a 1/3 left over here, and then minus 5 equals to 0. And you can always check, if you distribute this back, you can check that you get the function above, okay? Remember that when you multiply, you add the exponents. Okay, so now using zero product rule, we get two solutions, right? So x to the 4 over 3 equals to 0. That means x is equal to 0. So that's 1x intercept. And then another solution is x to the 1 over 3 equals 5 half, right? So that means that x by cubing both sides is going to be, what is it? 125 over 8. That's 5 cubed over 2 cubed. Okay. So we have this information here. Let's continue. So we have our x-intercept. So remember, those are the points 0, 0, right? So we obtain the point 0, 0, and we also obtain the point 125 over a comma 0. Okay. So at this point, it's just that I have to be scrolling up and down and so on. But it would be nice to start making a table. Okay, anyway, so what I'm gonna do is when it comes the time to graph, okay, I'm gonna first before graphing, I'm gonna have a little table in which I'm gonna summarize all the points that I'm finding. Okay, so for now, so I don't lose them later, I'm going to use blue for those points. So my y-intercept, so I can easily spot the points that I need. These are my x-intercepts. Okay, so later I can find them, my blue boxes. Okay, so we have this. Now let's go to step number 4, which is let's figure out the sign of the function. Okay, so the sign of f. So I remind you, let me write down the formula here for the function f, because, and the reason why I gave you these steps the way I gave it to you is just because notice that so far we are working with the same formula f. Okay, because if you start finding derivative first and so on, then you're gonna have a bunch of different formulas to deal with. And then if you want to find the sign of f, you could make a mistake and then use the formula for the derivative instead. And then you're going to get things mixed. So use the function f as much as you can. And once you are done with the function f, that's when you then move to the derivative. You use the derivative as much as you can. Once you are done with that, then you move to the second derivative and then you focus on that one. Okay? That way you control the formula you're working with and you're not going back and forth and then, because when you go back and forth, you can make mistakes and pick the wrong formula. So that's why steps 1 through 5, if you look back at the steps, notice that step 1, step 2, 3, 4, and 5, they all have to do with the function f. Okay? After step 5, we are done with the function f, like analyzing the function f itself. Then step 6, we move to the derivative. We do everything we can with the derivative, right? And when we're done, then we go to step 7, which is the second derivative, and then we're working with the second derivative. Okay? So it's a reason why I gave you that order, just to avoid possibility of mistakes later. Okay, so now let's find the sign of the function. As I mentioned, here really you don't have to do much work, okay? We basically have everything we need. So it would be kind of beneficial to have the factor version. So let me write down the factor version of this function, which is, we already have it on top. I'm just reusing information, okay? So now remember, how do we find the sign of a function? This is just a picture. All you have to do here is draw a picture. What picture? The sign picture, the one with the plus and the minuses and so on. So we do a number line, and then in this number line, what do we write? The zeros of the function, which we have them, right? Those are the x-intercepts. So we have 0, we have 125 over 8, okay? And just to get an idea, so what is 125 divided by 8? So that's about 15.625. 15.625. That way we know what that number is. Okay, when we're choosing our numbers. Okay, so we have this, and then we also need to plot the values that makes the function undefined. In this case, remember the function, the domain is all real numbers, so it's defined everywhere. So we just have to worry about the zeros, which are here. Okay, now let's pick points and put the sign of the function. Let's see, I'm gonna pick to the left. Let's pick here a -1 as a candidate, right? I'm gonna pick -1 here. Let me put it small. And then if I pick -1, actually let me use another color. Let's pick -1. So if I pick -1, then the first factor, notice that the first factor is always positive because it's x to the 4 over 3. Okay, and that 4 over there makes it positive. So it's really just the parenthesis. This parenthesis is the one that will tell us the sign. If I put a -1, the negative is going to survive, so we get -2 minus 5, so that's a negative. So the function is a negative here, okay? Then let's pick a number between 0 and 15.625, so let's say 1, right? Always pick easy stuff that you can plug in. So if you pick 1, so here I'm going to pick 1. So I'm picking this guy. Here I'm going to pick x equal 1. When you plug it in, we're going to get 2 minus 5, so we get negative again. Okay, we're going to get a negative again. And then on the other side, let's pick something that's bigger than 15. Now, because I'm doing cube root, okay, because that's 1 over 3, let's pick a perfect cube. And we know a perfect cube here will be 27, right? So let's pick 27. 27 3 cube. So remember, x to the 4 over 3, that's always positive, so we don't really look at that. Let's just look at the parentheses. So when you put 27, then we're going to get the cube root of 27 is 3, 2 times 3 is 6, so that's a positive. Okay, so this is our sign picture, our sign information for the function f. Remember what this means, okay? So this means below the x-axis, this is below, and this is above. Okay, so whatever the graph is doing, this is telling us what's happening. So for example, we know that at 0 we have an x-intercept, right? Now this is telling us that the function is actually below the x-axis around these 2 points. So what does this mean? So it means that we're gonna have, it's gonna be a touch point. We're gonna touch the point and then come back down, like when you're graphing polynomials and you have these points with even multiplicities, okay? Because the function has to keep the same sign around the 0. And then this is telling me that 125 over 8 is a cross point, because we need to cross the x-axis, because it goes from negative to positive. Okay, so this information is important, the sign of f. Okay, so now that we have this, let's continue. We know the sign, so let's just keep it there. There's no need to actually write down the intervals. We can see the intervals here in the picture. Okay. All right. So step 5, we want to figure out asymptotes. And I'm doing this, taking my time, doing it slowly, and explaining the steps, because that's the idea for this. So you see slowly how to graph the functions. But of course, you can do these things a little bit faster, when you're working on this. So let's find the asymptotes and then behavior. And behavior. Okay, so let's see. I'm going to actually, so let's look at the function. We have, we have the formula right there. To have a vertical asymptote will mean that first of all, we don't see any fractions here. So there are no obvious candidates, because there are no values that would make a denominator equal to 0. Okay, and also if you look at the expression, to have a vertical asymptote will mean that there is a special value that when you take the limit, you're going to get infinity, positive or negative infinity for this function. But no matter what number you take the limit of, you just plug in and you will get a number. Okay, also here is another hint. If the domain of the function is all real numbers, then in particular it's not going to have any vertical asymptote. Because remember, what does it mean to have a vertical asymptote? It means that's a forbidden point. It's a point so that when you get close to it, the function goes to the positive or negative infinity. So it cannot cross that line. But here you can plug in whatever you want. So this function is going to cross whatever vertical line you give it. Okay? So no vertical asymptote for f. And let me just say here, since its domain is all real numbers. Okay? So when you do the domain, if it is all real numbers, then that's it. You already know that you're not going to have a vertical asymptote. Okay? Now, if you get points at which the function is not defined, those are points that you should be considering, for your vertical asymptote purposes. Okay? So keep that in mind. Okay, so no vertical asymptote. So now let's look at the behavior. for the end behavior part, and remember, the end behavior will tell us if we're going to have any horizontal asymptote or not, and so on. Okay, so for the end behavior, we need to look at the limit as x approaches positive infinity of the function, and we'll also need to look at the limit as x approaches negative infinity of the function. Okay, so let's do this. So limit as x approaches positive infinity of 2x to the 5 over 3 minus 5x to the 4 over 3. Okay, so this is an infinity minus infinity situation, right? But we can easily solve this. That would be an indeterminate form, right? As infinity minus infinity. But one of the ways to deal with this is to actually factor. And we already know the factoring, right? We have done that above. Notice how many of the things that we need already has been done in previous steps. You just have to reuse that. Okay. So let's put the factor information. And now we see that this is infinity times infinity. So this is just positive infinity. Okay. All right. So we know that when x approaches positive infinity, the function goes up to positive infinity. And now here is a similar thing. So we have 2 times x to the 5 over 3 minus 5x to the 4 over 3. Once again, when x approaches negative infinity, we're going to have this part here goes to negative infinity, but then this one is going to go to minus positive. So negative infinity. Okay, this is negative infinity, and then this one is going to be minus, and then x to the 4 over 3, that goes to positive infinity because of the 4. So this is negative infinity minus infinity. When you subtract two negatives, that's still negative. So the answer here is a negative infinity. Okay, that's not an indeterminate form. The determinate form is infinity minus infinity, but this one is negative infinity minus infinity. That's different. Okay, if you subtract two, if you subtract two infinities, I guess if you add two infinities that are negative, you get negative infinity, because this is the same thing as negative infinity plus negative infinity. Okay, so that's just negative infinity. So no need to actually factor, but if you want, you can look at the factor version, and then you will get positive infinity times a negative infinity, which give you negative infinity. Okay, however you want to look at it. Okay, so we know how to begin the graph. We begin at negative infinity, and how to finish the graph. We begin at positive infinity. So our picture is going to begin in quadrant 3 and finish in quadrant 4. So what this is telling us is that whatever the graph is, it's going to come from here, and it's going to finish up here. Okay, that's what this is telling us. Okay, so we know the end behavior. Let's see. Yeah, later when I tell you about about slang asymptote, you will see, but this function doesn't have a slang asymptote. Just, I guess, a very quick hint, and then I will expand on this later. For the slang asymptote question, let me not use blue. Because when you get infinity for the end behavior, this means that no horizontal asymptote. So let me say, so far, this is telling us that no horizontal asymptote. Okay, but then you may wonder, okay, do we have a slang asymptote? Well, for the slang asymptote, I'm going to explain why this is later. Or you can take it as a black box for now, what I'm about to tell you, and then you can ask me, you know, you can ask me in class why this is the case. It's really simple to figure out whether you have a slang asymptote or not. So slang asymptote is, it means that is our function looking like a line when x approaches infinity. Okay, so is a function getting close to some line? So it's the end behavior of the function resembling that of a line when x approaches, positive or negative infinity. So let's call this line y equal mx plus b. So to find such a slang asymptote, if it exists, is, what you need to do is find m and find b, and then you're good to go. I'm gonna give you the way to figure out m. So m is actually found by taking the limit as x approaches either positive or negative infinity. You have to see which one you're looking at, okay? So let's see, let me give you a formula. As x approaches either positive or negative infinity, so these are really two limits that you need to find, okay? Because you could have more than one slang asymptote. For example, think about a function that may do this. You have this line, you have this line, and then this is your graph, okay? For example, think about this kind of functions. This would be a function and it has two slang asymptotes, okay? This one and this one. So one going to positive infinity, and this other one is when it goes to negative infinity, okay? So that's why you have to take both limits, okay, of the function divided by x, okay? So you take this limit, the two limits here that you need to take. If this limit equals a number, okay, then you have a slang asymptote, and that's the slope. Then you just need to figure out b, okay? But if the limit is not a number, then you move on, okay? That means that there is no slope. Basically, what we're saying here is that slope-wise, our function behaves like the function x, right? It's like at the same rate as the function x, so that's how you detect that a function looks like a line at infinity, okay? So if this limit is finite, so if this limit exists, meaning it's finite, then we have a slang asymptote, and the value of the limit and its value is the slope, okay? So let's say that you found that the limit exists either positive or negative infinity. You need to decide, you need to record which one is it. Is it the positive or the negative infinity? Then the question is, okay, the limit exists, therefore we have a slope. Now what is b? Well, to find b, but you first figure out the slope. If it exists, then you go to step 2. If it doesn't exist, the slope, then that's it. You stop, because that means that there is no slang asymptote. Okay, and then b is gonna be, if this limit exists, then we have slang asymptote and its value is the slope. Otherwise, there is no slang asymptote. Okay, and then to find the b, all you do is the limit as x approaches, the same infinity that you were doing, either the positive or negative infinity. I'm gonna put here both because it really depends which one you use above. So if you use positive and you got a number, then you use positive here. Okay, if you use negative and you got a number, then you use negative, and then you do the function minus mx. Okay, so notice that you already know the slope. If you're in step 2, it's because you already found m. So then you can look at m times x. So look at the difference of the function on mx, and then this will be a number. This number is b. Okay, all right. So that's how you find slang asymptotes. Okay, it's a brief synopsis. Let me box this. So you can take this now as a black box, or I guess a green box. So when we use this expression of black box, is okay, here is a fact that I'm giving you. Just some formulas, just take them for granted for now, work with them, and then later I will explain to you why these formulas make sense. Okay, but right now, for the sake of time, let's just take it as a black box. So here are some formulas that you can use, and I kind of have given you a hint of why these formulas make sense by talking to you. Okay, if you were able to pick up on that in the explanation before. Okay, anyways, we want to figure out whether our function has a, we know the end behavior is infinity, but is it a linear infinity or not? Well, that would mean whether it has a slang asymptote or not. So let's see. If it's gonna have a slang asymptote, then we need to compute the limit as x approaches infinity. Let's look at what happens at positive infinity first, of the function divided by x. Now, the function divided by x is, so our function is 2 x to the 5 over 3 minus 5x to the 4 over 3 divided by x. Notice when you divide by x, what do we get? I'm gonna get 2 times x to the 2/3, so 5 over 3 minus 1, that's 2 over 3, minus 5, 4 over 3 minus 1, that's 1 over 3. So notice that, the x survives, so we actually, we are not gonna get a number, okay? So we're gonna get also some type of infinity. Let's see, here we have infinity minus infinity, but again, we can do the same thing. We can factor. This time the lowest exponent is 1 over 3, so we take out 1 over 3. So we get 2x to the 1 over 3 minus 5. Okay. And then this is infinity times infinity, so it's going to be positive infinity. So that means no slang asymptote, at least in this direction. Okay. But now notice that if you do negative infinity, so similarly, the same thing that happened above is going to happen. If you try to look at the limit as x approaches negative infinity of the function, what is it that we're going to get? So it's exactly the same expression that we have here, factor. So we're going to get exactly this same expression. And then this time there's going to be negative infinity. Let's see, that will be a negative infinity times a negative infinity. So we also get positive infinity. So no slang asymptote either. In this direction. Okay, so our function doesn't have a slang asymptote, so we move on. Okay, so we just begin from quadrant 3, finishing quadrant 1, but there is no linear behavior. Okay, in this M behavior. Okay, so that's how you find how do you determine whether you have slang asymptotes or not, and if you do, then this is how you find them, what is inside the box. Okay, all right, so notice that we have done all we could with the function f. Okay, now it's time to do more calculus, which is now let's go to the derivative. So step 6, and here we want to find f prime. Okay, because okay, let me just write that here. We're gonna find concavity and relative extreme. No, monotony. So monotony, relative extreme. All right. So for this, we need to look at the derivative of f. So let's see. The thing is that you need to have the function in mind. So let me say relative extrema of the function f of x, which is 2x to the 5 over 3 minus 5x to the 4 over 3. Notice that I'm putting this in the title because I don't want this to be mixed with my computations. Okay, so for that, we know we need to look at the first derivative, so let's do it. So it's going to be 2 times 5 over 3x to the 2 over 3, just subtract 1, minus 5 times 4 over 3 x to the 1 over 3. Okay, so that means the first derivative is 10 over 3 x to the 2 over 3 minus 20 over 3 x to the 1 over 3. Now, once again, here you want to find zeros and so on. So it's good practice to have this in a factor version. So let me factor the derivatives. So here I'm going to take out a 10 over 3. And then the lowest exponent is 1 over 3. In the first parenthesis, we're going to have an x. In the first term, we have x to the 1 over 3 left over. And then the second term, we're going to have a 2 left over. You take out 10 over 3 from 20 over 3 and you get 2. Okay. So now we need to find the critical numbers, right? So what are the critical numbers? Remember two things. F prime undefined. In this case, we don't get anything, right? The root is defined everywhere. Those are cube roots, and there's no fraction here. And then the other one comes from derivative equal to 0. So we need to solve this equation. And then the solutions are apparent here. So we get x equals 0 coming from this guy. And then the other one will be x to the 1/3 equals 2, meaning that x is 8. That's coming from this other guy. Okay, so we found ourselves two critical numbers. So these are the ones that we're gonna have, because now remember we want to find the sign of the derivative. So here is another sign picture, and here what do you put? You're gonna put the values that makes the derivative 0 or undefined. We didn't find anything that makes the derivative undefined. Now we find values that made them 0. Check these guys, and let's test for sign. So again, I'm gonna use, let me put the numbers that I'm gonna use here. Let's use -1. I'm gonna use 1, and then because I have cube roots in there, I'm gonna keep using my 27 over here. Okay, so let's see. So if you plug in -1, we're gonna get a negative. Let's see, we get a negative in the first term times a negative in the second term. So that's a positive. If you plug in 1, I'm looking at the factor version. Okay, if you plug in 1, you're gonna get a positive in the first factor times a negative in the second factor. So that's a negative here. And then if you plug in 27, you're gonna get 3 there, so that's 10, so that's a positive, and then 3 minus 2 as a positive. So we get a positive here. So remember, this is the first derivative. So what is this telling me? This is increasing. Here the function is decreasing. And then here the function is increasing again. So we immediately can now determine the relative extrema. We have the monotone in this picture. No need to actually write all the intervals, etc., because this picture is telling us everything we need. Now here we can see that this guy is, notice that these points are on the domain. Domain is a real number, so we care about everything here. So this is now a relative max, right? And this one here is a relative mean. Okay, because again here you can think of the function as doing this, and here you can think of the function as doing this. All right, okay, so we have ourselves a relative maximum and a relative minimum. So again, those are important points that we found. Okay, so they are gonna go to my blue boxes. I guess I'm gonna record here also a monotony. So increasing, that will be from negative infinity to 0, then also from 8 to positive infinity. Decreasing, that will be from 0 to 8. And then we also have some points. We found ourselves relative maximum at 0 comma f of 0. And so here it's important that you plug in into the function, the original function, because these are points on the graph. And relative minimum at 8 comma f of 8. So let's look at the formula, which is up here in red. So f of 0 is 0, as you know. So as a point 0, 0 is a relative maximum. And then what happens if I plug in 8? Okay, so 8 is a perfect cube, so that's good. So when you plug in 8, what do we get? Cube root of 8, that's a 2. So that's going to be 8 to the 5th power times 2. Then minus 5 times, that would be, no, it's not 8, it's 2 to the 5th power. Wait. Okay, 2 times 2 to the 5th, then minus 5 times 2 to the 4. Okay, so this is a negative 16. Okay, all right, that's a nice little point. So we found, I mean, we already have 0, 0 from before in our table, but now we know 0, 0 is a relative maximum, but we found a new point to have in our graph, which is a relative minimum, right? Which is the point 8 comma negative 16. So let's put that on blue box. Okay, so now that we have everything about first derivative, then let's go to our seventh step, which is looking at the second derivative. And for that, we want to figure out concavity plus inflection points of the function f. Remember, this is about the function f. So of the function f, let me remind you the formula here once again, which is 2x to the 5 over 3 minus 5 x to the 4 over 3. Okay, so we want to find this information. Now we know this data lies in the second derivative, but to get to the second derivative, remember what we need. We need to first find the first derivative. We already have that from the previous step, so let's copy that. Now here, it's not good to write down the factor version because then you either distribute or you have to do product rule. Okay, so might as well to use the non-factor version, which is the one that we have above. So I'm gonna use that one. 10 over 3 times x to the 2 over 3 minus 20 over 3 times x to the 1 over 3. Okay, so that's our first derivative. And now we look at the second derivative, which is 20 over 9 x to the negative 1/3. We subtract 1, then minus 20 over 9 x to the negative 2/3. Okay. All right, so now remember, negative exponents are kind of deceiving, so make sure that you write them in the denominator and then you combine. Now here, this is 20 over 9, so it's begging for you to factor it, so let's do it. So let's factor 20 over 9, and then here we're going to have 1 over x to the 1/3 minus 1 over x to the 2 over 3. And now we just need to combine these two fractions. Remember, all we need to do is make the denominators the same, and we can easily do that by multiplying the first one top and bottom by x to the 1 over 3. Okay, this is so that we can make the denominators the same. So we get that our second derivative then is going to be 20 over 9 times x to the 1 over 3 minus 1 over x to the 2 over 3. Okay, so that's our second derivative, and now we have it in a form that is very easy to analyze, zeros, undefined, etc. Because remember, our job now is to find the sign of the second derivative. But for that, we need to find the zeros, which is given by this equation. Those the zeros at the top, which will be x equal 1, and then undefined. What is the second derivative undefined? Well, this time we get that is undefined at x equals 0. So sine of f double prime. Now we're gonna put this information here. So here is a 0, and here is 1. These are the numbers that we found. And then, let's plug in. Again, let's pick our test point. So here I'm gonna pick -1. Here I'm gonna pick 1. Instead of 20, I mean, you can keep picking 27 if you like, but for example, 8 is a smaller guy that I can pick. That's a perfect cube. So let's pick it. All right. So if you put -1 here, what's going to happen? The top is going to be negative. By the way, notice that this bottom here is always positive, right? Because of the square. Because the 2 over 3, the 2 in the numerator, that's the square, so that makes things positive. So really, the numerator is the one that tells me what's going on. So you put a -1, you get a negative. You put a 1. Oh, I don't know why I wrote 1 here. Should be like 1/2. Okay. So you put a 1/2. Actually, let's make it easier. Let's put 1/8. It's a perfect cube, right? So you put a 1/8, then you get 1/2. 1/2 minus 1, that's a negative. So let's do negative here. And then you put an 8, that's a 2. So 2 minus 1, that's positive. So that's a positive. So that means that here we have concave down, and then here it goes to concave up. So that means that 0 is not an inflection point, okay, because there's no change in concavity around 0, but this guy right here, 1, is an inflection point, okay? So let's go to our blue box. So for the concavity, we found that the function is concave down on the interval from -infinity all the way to 1. The function is concave up from 1 to infinity. And then we found an inflection point, which is the point 1 comma f of 1. Remember, always plug into original function. If you plug in 1, we're going to get 2 minus 5, which is -3. So that's the point 1 comma -3 is an inflection point, our blue box. Okay. All right. So we did step 7. So we found concavity inflection points. Now we have everything we need. So step 8, let's put all of this together and let's finally produce a picture. So step A, sketch. Sketch the graph of, and let me repeat the formula here once again. So what's the function f is 2x to the 5 over 3 minus 5x to the 4 over 3. Okay, so let's sketch the graph. Now let me put here a table of values that we have found. Okay, so I'm gonna have here my point, and then I'm gonna put here type, which is, you know, what sort of point are we talking about here. So here, this is everything that I found in my blue boxes. Okay, so table of values. I'm just gonna summarize now the information that I found, because, you know, I have too many things going on. When you have a paper, it's easy because you just look at it and that's it. But here we need to go up and down. I don't want to be doing this all the time. So let's see. We found 0, 0 and 125 over 8 comma 0. So 0, 0 and 125 over 8 comma 0. So those are points to be considered. And remember, this is x-intercept, and also it was a y-intercept. This one is an x-intercept. Okay, so that was that. Then we have another blue box. So we found 0, 0 is also a relative max, and then 8 comma -16 is a relative mean. So relative max also, then 8 comma -16, this was a relative mean. Okay, and then we found 1 comma -3 is an inflection point. So these points that are here, they are a must in our graph. They need to show up. Okay, they need to show up, indicating, you know, what they're doing. Now, as we graph, we may need to plot a couple more points, you know, to get a more accurate picture if you want to. But these points right here that you see, they are a must on our picture. The others are really optional. We are sketching anyways. We're not exactly graphing. So since we are summarizing information here anyways, so let me put the things that we need. So for example, I want to have the sign of the function. I want to keep this, so let me make this handy for us. Copy this. Okay. I'm gonna have it here. This is, remember, this is the sign of F. This is the sign of F. Now I want to have also when it's increasing, I want to have when it's decreasing, I want to have when it's concave up, and I want to have when it's concave down. Now here in all of this, we actually have, you know, most of the information. We already know the end behavior from the top, so I don't need to rewrite it here, and there are no special asymptotes. So let's see, increasing, decreasing, increasing, negative infinity to 0, and 8 to infinity. It's coming from the blue box, negative 8 to 0, and then 8 to infinity. So negative 8 to 0, and then 8 to infinity. Then decreasing, oh, negative infinity to 0, and then 8 to infinity. And increasing was from 0 to 8. Yes. Then concavity, concave down, negative infinity to 1, concave up, 1 to infinity. Okay, so let's see. Let's graph. Now, I don't need to scroll all the way. I just have to scroll a little bit. Okay, so now here I'm gonna do a big graph so we have space for everything, and also, you know, also try to have, a reasonable scale if possible. And my scale is not gonna be, I mean, we'll see, because remember this 125 over 8, that was 15.625, so we have to go all the way to 15 and so on. So anyways, let's plot our points. Let's see, 0, 0. So that's a point of interest. So a point has to be there, 0, 0. Then 120. So if we had any asymptotes, by the way, and now when it comes to time to graph, the first thing that you do is put your asymptote. Vertical, horizontal, slant, whatever it is, just draw your asymptote, remember, with dashed lines. Once you have them, then start pulling your points of interest, which is what we're doing right now. Okay, 125 over 8,0. All right, first, I guess, let me do the small ones. So 1 comma negative 3. Let's say I'm gonna put the 1 here and the negative 3. I mean, this is not gonna be up to scale, because otherwise we need too much space. Let's see, 125 over 8. I'm just gonna stick it over here. Okay, I know this is not 15 from 0 to there. It's not 15.625, but I need either a very tiny unit length or a very long x-axis, and then the picture will be uncomfortable. So we're just sketching anyways. That's the next intercept. Okay, then 8 comma negative 16. That's a relative minimum. So 8 comma negative 16. All right, so 8, I'm gonna put it more or less halfway here. Okay, comma negative 16. Okay, I'm just gonna put negative 16 here. Again, we're just sketching, okay? And if this bothers you too much, then I guess let's put the negative 3 somewhere in here, like a little bit closer. Just I don't want to be super close to 0, 0, because then our graph is gonna be uncomfortable, okay? Now we just want to create the sense of how the graph is gonna look like. Okay, so we have those points. This was 8. And what else? That's it. So now notice that you see, even if we don't want to, notice that there is no point on the negative part. And when we come from the negative side, we want to know more or less where to go. So it's a good idea to pick something. So I'm gonna pick something easy to plug in. Let's pick -1. Let's see when x is -1, what's y. So this is when you will see that, okay, I need some more additional points just for to make my graph easier. Anyways, we put -1, then we're gonna have 2. So -2 minus 5, so that's a -7. So this is just an extra point. Okay, extra point. So that's -2 minus 5, so that's a -7. So I know that, let's see, somewhere halfway, a little bit here. Let's put here -7. The point, we need to go through the point 1 comma -7. Okay, because we know that we begin here because of the behavior, right, and finish up here. But I'm not gonna do this kind of stuff. I know that I have to go through this point. Okay, and if you want more precision, then you find more points, but 1 point at least is enough. And notice that we're gonna go through 125 over a, and then we don't have anything else. But let's see, if I put 27, I think it would be too much. No, that's a 3 to the 5 or 3 to the 4. Let's see what happens at 27. If I plug in 27, I'm gonna get 3 to the 5, so 2 times 3 to the 5 minus 5 times 3 to the 4, which is an 81. Okay, so we get 81. Okay, so that's 27,81. That's another extra point. If we don't have any other nice point. Okay, so I guess when I graph, I'm just gonna say up there I'm gonna have 27. Let's say up here somewhere. I mean, it should be more to the right, okay? But that's my 27,81. Okay, so I will go through that point as well. All right, so that's enough. Time to start graphing. Again, let's put this in perspective. So we're gonna come from down here, and we need to finish going through this point up here. Okay, let's start now joining everything together. So the function is gonna be below the x-axis all the way up to 125 over 8. Okay, very good. Then let's see, what do we do? It's gonna be increasing from -infinity to 0, and we need to go from -infinity to 0. We do that in a concave down way because it's concave down from -infinity to 1. Okay, so I'm gonna come in a concave down way and do this. Okay, so it's doing that. Then we know that we have to touch 0 because that's an x-intercept, but then it's also a relative maximum, and we need to come back down because we're still negative, and we need to create a maximum. So let me create a maximum there. Okay, something like this. Then we need to go through 1 comma -3, and notice that that is an inflection point. And what's happening there, let's go to our sign. At 1, we have a change of concavity. It goes from concave down to concave up. Okay, so we need to kind of make that clear. So let's see, down, then sort of, I want to concave down, and then it becomes concave up. So from down to up, like that, something like that. Okay. Even if it's not super clear, we just label it, as I mentioned in class. So right now, once we finish graphing, we're just gonna say that we have an inflection point right there. Okay, so it changes to concave up, and then what happens at this point? We need to go all the way down to negative 16, 8 comma negative 16. That was a relative mean, okay? And we need to do that in a concave up way all the time. So, okay, so we have to do this in a concave up way. And then after 8, our function starts increasing, right? Because now the function is increasing from 8 to infinity. So now it's increasing all the time. And notice that we have to be, so after x equal 1, we are concave up all the time. Now we go increasing like that. And it appears that, I mean, the graph is kind of forcing me to do this. So I guess, and so yeah, it's just that, 27 is far away. So you have to go ultra super up to show the 27,81. So I'm just gonna say, no, it's gonna be too weird to say that that's 27. So I'm just gonna keep it like that. So if you want, just ignore this point, but it's good to have it in the table. But I'm not gonna plot it. Okay. So I guess something that's not clearly specified here, I'm gonna do it, is the fact that this point right here is in the table, but on the graph, I want to emphasize that that's an inflection point. So we're supposed to be changing concavity there. Okay. Let's see, there is a weird thing happening here. Let me fix it. Okay. So this is more or less how the graph looks like. This is a reasonable sketch. We have all the necessary information: our relative minimum, our relative maximum, our inflection point, our zeros, and the concavity, increasing, decreasing, etc. Okay, again, I know this was quite long, but it's because I'm explaining everything one step at a time, etc., etc. But hopefully you saw how we put together all the information to produce a graph. Okay. All right. So what I'm gonna do is I'm going to pause this video so that you can see this complete picture, right? And then I'm gonna create a new video right away. So there will be multiple videos, like maybe 2 or 3 videos today. I think 2 videos. Now I'm gonna create another video in which I'm gonna do 2 more examples. But I just don't want to overwhelm you with a lot of information in one single video. So once you watch this video, you're gonna have the general steps explained that I explained at the beginning, together with one full example. Now I'm gonna create a new one with 2 more examples. Okay, one of them with a trigonometric function, and then another one with a function in which we have a vertical. We're gonna see that we're gonna have a vertical tangent line. I want you to see how to deal with that case. Okay. All right. So I will be doing the second video now.